We have some non-human attendants.
Yes, I have a dog. Hopefully he'll be not too distracting. He was napping.
What kind of dog?
He's an Australian Shepherd. He's in the back room, but he can be pretty loud. I also have a cat, and he's here now.
Very nice. Are they fans of the monsoon?
Of course. Big fans.
Say this is bring your pet to work day.
Always.
Okay. Let's get started. Welcome everybody to the Monsoon Geo Seminar. Today we have Samantha Carter who will be talking about strontium and neodymium isotopes and on the Indus Fan. Samantha finished her PhD at Ohio State University, and now she's doing a postdoc combining her work between Ohio State and Santa Cruz. She's been working on the Indus Provenance from IODP Expedition 359. Am I correct? 357?
55.
355. And she's been working on productivity before in the ocean, and now she's working on calcium isotopes, very interesting in isotopes and dolomites. Welcome, Samantha, and please start your presentation.
Thank you. Let's see here. Okay. So, like he said, I'm going to be presenting some of the work that I did during my PhD dissertation, which looked at strontium and neodymium isotopes in the separated clay fraction of sediments from the Indus Fan. So I will just introduce the area briefly. So the samples from this study come from Expedition 355, the Arabian Sea monsoon. We've probably heard some talks using samples from this expedition, but this expedition drilled two sites, U1456 and U1457, that are located in the Indus Fan. So the Indus River here is the main source of sediments, and this drains kind of through the Himalaya. You can see there are also these a couple smaller peninsular rivers here that drain through the Deccan traps. So these could also be contributing sediment to these two sites. But overall, this expedition was kind of designed to achieve a better understanding of erosion and weathering in the Himalayas and how this corresponds to changes in the intensity of the Asian monsoon. So I'm going to be looking at provenance, so the source of erosion, and how this might correlate to monsoon intensity. So this is a map showing modern annual precipitation patterns, and you can see it's a little different. So we have India here, the Arabian Sea over here, so the sites are kind of down here somewhere. But the Asian monsoon tends to control erosion in this region. So where the sediments are eroded from is correlated to the intensity of the monsoon, at least in the modern day. In normal years, you can see by these dark blue patterns, the larger amounts of rainfall are kind of concentrated in lower elevation areas of this Himalaya, so along the Himalayan front. And then the study went on to show that during years of a more intense monsoon, this rainfall tends to conquer these orographic barriers, and it kind of pushes further up into these higher elevation areas in the Himalaya. So I'm going to track provenance using strontium and neodymium. So although kind of neodymium is a very useful proxy for provenance because it's not significantly altered during erosion and weathering, whereas strontium is a little more complicated because it can be sensitive to these other types of processes. However, I'm going to be kind of careful and kind of step through the other processes that might be affecting the strontium isotopic record. And I think it's still really useful to use both of these in combination because we can kind of further distinguish between these potential sediment sources. So this is the map shown previously, now overlain with the major geologic units in the area, and then their strontium and neodymium isotopic compositions. So you can see there is this nice relationship between kind of where they plot out versus where they are in the Himalayas. So the volcanic rocks in blue, these have high epsilon neodymium values and low strontium compositions. And these tend to be in the higher elevation areas of the Himalayas. Whereas these granitic rocks shown in shades of red, these tend to have lower epsilon neodymium, higher strontium values, and these are in the lower elevation areas. So these are along the Himalayan front. And then of course we have the Deccan traps here that have values similar to those rocks in the northern Himalayas. So those will come up later. So provenance is important to understand for a variety of reasons. It's important to understand sediment pathways. So how are these moving, or how are these sediments kind of moving through the riverine system and into the ocean? And how does this change over time? Links to climate and tectonics. Like I said, the Asian monsoon is the major control of erosion in this region. But of course, this is a very tectonically active area. So it's important to kind of think of those events as well, because that controls kind of what units are exposed at the surface and therefore what's eroding. Also very important to constrain other paleo records that are produced from these same cores. So we need to determine if other records are being controlled by changes in provenance, or if they're actually showing changes in whatever proxy they're trying to reproduce. So I'm going to take this kind of one step forward. So provenance is traditionally reconstructed using the bulk sediment, so the whole sample that's not separated by grain size or composition. But the provenance from the bulk sediment can be biased in certain depositional settings because physical fractionation can occur as these sediments are transported through the riverine system and deposited into the ocean. So bulk sediment can be kind of spatially heterogeneous because those larger dense minerals tend to settle out more quickly and they concentrate in bed loads, while those smaller, less dense minerals are kind of transported in suspension. So there's different mineral phases that can strongly control the strontium and neodymium isotopic compositions, and those can be enriched or depleted in different grain size fractions. So in this study, I'm going to analyze or look at just the separated clay fraction. Because clays settle out of the water column at a much slower rate, they kind of travel further and more quickly through the riverine system. So they actually have transfer times an order of a magnitude shorter than those of the coarser fractions. And because of the large distance between the Indus River mouth and these study sites, we're hoping that there be less influence of this hydrodynamic sorting in this clay size fraction. Also, clays are formed in the weathering environment, so they kind of reflect the overall composition of what's being weathered at the time of alteration. So they kind of integrate the riverine system signal. Sorry, my cat is dropping things. We'll deal with that later. So the clay minerals integrate the riverine signal rather than being affected by a particular mineral phase. So I separate the clay fraction and analyze that, and then I'm comparing it to bulk records from samples that are just adjacent, sorry about that, to the samples that are shown here. So they're either right next to each other or they're within 2 centimeters in the core. These 2 records from the clay fraction and the bulk sediment. So I analyzed samples from both cores. Most of them come from U1457 with a smaller amount from U1456. I do have a bulk grain size record, and I separated out the less than 2 micron fraction kind of using a modified method. So you can see that distribution of that clay separation method here, where you have grain sizes less than 2 microns, with nothing larger than that. Then I dissolved those clays, measured potassium aluminum ratios to kind of consider chemical weathering changes. And then I analyzed strontium and neodymium isotopes, mostly on a thermal ionization mass spec, but some also on a multi-collector ICP-MS. So kind of thinking back to those overarching objectives of the expedition. So I'm going to be using the clay fraction records from these 2 sites to determine kind of erosional patterns and how that links with the monsoon. However, in order to reliably make interpretations of these proxy records, we really need to think carefully about the other processes that might be affecting these sediment samples. So I'm kind of going to go through each of these different processes and look at how they're affecting the record that I show here. First, I'll look at sediment transport. So this is just how sediments are moving through the riverine and ocean system and how they're affected by that hydrodynamic sorting. So this is a kind of a complicated figure showing a lot, but I'm just going to focus in on a couple different things here. But this is a correlation matrix. So it's just showing the how strong a correlation there is between 2 different records. So anything in red is a strong negative correlation, pink is weak negative, and then blue is strong positive correlation, and light blue weak positive. And anything bolded is significant at the 95% level. So I'm just going to focus in on a couple relationships. The first is the relationship between the bulk sediment isotopic records and the clay fraction isotopic records. So you can see here is the strontium bulk and clay comparison, and then here's the neodymium bulk and clay. So they are both positively correlated. It's stronger for neodymium, it's 0.9 here, than it is for strontium, which is 0.6. And this is probably due to kind of the other processes that can affect that strontium isotopic record. However, there is still a strong correlation between strontium and neodymium. So if we look just above this box, this is clay strontium correlated to clay neodymium. And there is still a strong correlation here. So because that neodymium is not as sensitive as strontium to these other processes, neodymium is strongly controlled by provenance. A strong correlation between these 2 suggests that strontium is also dominated by provenance here. But I'll kind of look at other processes as well. Now, kind of focusing in on the isotopic records and how they correlate to average grain size. So you can see the bulk records are more strongly correlated to grain size, whereas the clay records are correlated, but only a weak relationship. So we can look at cross plots of these. So So we have grain size here on the y-axis, and then the isotopic records here on the x-axis, with the clays on the left and the bulk sediment on the right. So there are positive correlations in the clay and bulk strontium records with grain size. And this is probably caused by this hydrodynamic sorting that we were talking about. There's a positive correlation seen between strontium and grain size that's shown in riverine systems. And this is just because the more radiogenic phases tend to concentrate in a coarser fraction. So this has been observed in several different sediment types. Relationship between neodymium and grain size. So this just suggests that more radiogenic phases are concentrated in a smaller size fraction, so kind of opposite to strontium. But this relationship has not been shown to be consistent with other sediment types from previous studies. And so this relationship can be variable. This figure here shows here on the y-axis, you can see this capital delta strontium and capital delta neodymium. So this is the magnitude of the difference between the clay and bulk sediment records. So just the clay minus the bulk, and then the absolute value of that difference. So you can see that the difference is correlated with the bulk records for both strontium and neodymium. So these are the bulk sediment records, and we have R values larger for the bulk than for the clay. So it's that heterogeneity of that bulk sediment that tends to cause differences between these two isotopic records, between the bulk and the clay in same sediment samples. When we look at that correlation with grain size, so this is that difference between clay and bulk correlated with grain size, you can see both have a positive correlation with grain size. So basically, as the grain size gets larger, that heterogeneity of the sediment's isotopic composition tends to increase, and the difference between the bulk and the clay is larger. Here I am looking at replicate analyses of the same sample from the clay fraction. So you see strontium on both the X and Y axis. So this is from replicate analyses. So basically I just digested or redigested the clay fraction and reran for the isotopic value. So sediment heterogeneity leads to a lot of difficulty in reproducing isotopic values. So it's hard to get the same value for replicate samples. And strontium isotopes in particular have been shown to be very difficult to reproduce in sediments. So having these replicate analyses kind of reduces the uncertainty of your data. So it is important to have good replicates. So you can see here, sorry, again, cat. Normally he's not this loud. I don't know what's going on. But you can see this black line is a 1-to-1 relationship, and the clay fraction does reproduce quite well. And we can compare this to other size fractions. Oops. Yeah. To other size fractions from another study from Janelle et al., who looked at the bulk sediment as well as larger size fractions, although she didn't look at the clay size fraction specifically. But you can see that, so here on the x-axis is the difference between replicates, and then these large x's are the average difference in each grain size fraction. And you can see the clays done in this study are able to be reproduced much better than the other size fractions. So this heterogeneity of this sediment is not as influential on this clay size fraction. Next, looking at chemical weathering. So here I'm showing the potassium aluminum ratios from the clay fraction, as well as are compared to the strontium and neodymium records. Potassium aluminum is traditionally used as a proxy for weathering, although it's known to be affected by other processes like sediment transport, as well as provenance. But we're just going to kind of compare to see if strontium is affected by chemical weathering. So you can see here that there is a weak positive relationship here between strontium and potassium aluminum. So if strontium isotopes are influenced by weathering, you would expect sediments to have higher strontium 87, 86 values if they are more intensely weathered. So if both of these records were affected by weathering, you would actually expect a negative relationship. So because we see a positive relationship, it suggests that potassium aluminum is actually affected by something other than weathering, rather than strontium being affected by weathering. So here we show that strontium is not dominated by chemical weathering. You can see neodymium has
Did we just lose Sam?
It seems that we lost Sam. I'm going to send an email.
I'll text her real quick. Yeah.
Let's just wait a couple of minutes.
hello. Okay. Great. Sorry about that. Got kicked off. I just need to have screen sharing enabled.
Done.
Great. Thank you. Okay. Sorry about that. I don't know when I got kicked off here. Did I finish talking about diagenesis?
No, not yet.
Okay. I think I was talking to myself for a little bit before I realized I got kicked off.
You are on a slide before this.
This
more. Yeah, that's it.
here. Okay. I'll just finish up here.
Did the cat cut the connection?
No, it wasn't the cat. I don't know.
Okay.
Okay, so looking at chemical weathering, let me get my bearings here. So we have this weak positive relationship, but if strontium was influenced by weathering, you would expect sediments to have a higher strontium 87, 86 value if they undergo more intense chemical weathering. So you would actually expect this relationship between potassium aluminum and strontium to be negative if they're both being controlled by weathering. So this positive relationship suggests that strontium is not dominated by chemical weathering. Rather, this potassium aluminum is probably controlled by something other than weathering, like that sediment transport processes. And you can see here, the neodymium record shows no correlation with potassium aluminum, which is what we'd kind of expect. It's more strongly associated with provenance. And then lastly, before we move on to provenance, we'll look at diagenesis. So this is how the sediments are altered after they're deposited. So in a previous study, I looked at the strontium isotopic composition of pore fluid from these same two sites from 1456 and U1457. So that's what's shown in blue is the composition of pore water. And then in green, we have the clay values from this study. So I use strontium as a proxy for diagenesis because it's more sensitive to diagenetic changes as compared to neodymium. So if these sediments were strongly affected by diagenesis, you would see these variations reflected in the pore fluid. It would look more like the pore fluid values. So you can see there's really no significant influence on these clays by diagenesis. However, you do see in Unit 2, we have this strong increase in the isotopic composition of the pore fluid values. So these are sediments within the methane generation zone. So it looks like the dissolution of these siliciclastic sediments is affecting the pore fluid strontium, but not necessarily vice versa. And finally, we'll get to provenance. So this is the cross plot showing the geologic units as well as my samples here as these points. So what I did here is I did a statistical cluster analysis to cluster the data based on their unique isotopic compositions. And what that did was split the data into these two clusters. Cluster 1 is shown in blue, and those are those more primitive volcanic sources that are located in the higher elevation areas in the Himalaya. And then in red here are those lower elevation area granitic sources. You see mostly a linear relationship between these two. So that just suggests kind of a simple mixing of these two basement sources. You do see this one value way up here in green. This value is from the lowermost unit 5 from the core, which actually predates the India-Eurasia collision. So we would expect the provenance of this particular sediment to be very different. It's either a Deccan trap source or there is some evidence of sediment alteration by the basement rock. So I won't talk anymore about this unit 5. I'm going to focus on these samples here. So now we're looking at the 4 records compared with age, so how they change through time. And in each of these, this black line shows the 5-point running average. And then these light gray envelopes in these 3 records are actually the error that's derived from replicate analyses. So you can see for potassium aluminum, replicate analyses weren't reproduced great, which is why we have a larger gray envelope, light gray envelope. You can see it's pretty much it's very small for strontium isotopes because those clays were reproduced reproducing the isotopic values so well. I didn't run replicate analyses for neodymium, so I'm using an error from a previous study from Janelle et al., and that's what's applied to the neodymium record. The dark gray envelope is the 5-point running standard deviation. So this is just showing kind of how variable the samples are with time. So when we have a smaller dark gray envelope, the samples are much more closer together with time, and then larger, meaning more variability. So I'm going to focus in on a couple different time periods. First, from 9 to 5 million years ago, we have this kind of overall trend towards more negative neodymium values and higher strontium 87, 86 values. So this would suggest kind of an overall increase to a predominantly more Himalayan source, so those sources in the lower elevation areas. So along this Himalayan front. So we have more erosion coming from here throughout this time period. And this is interpreted as a weakening of the monsoon because we have decreased rainfall penetration into these higher orographic areas. And this agrees with kind of other records from this area that show increased in aridity over this time period. And then you will notice around 7 million years ago, there's this transition. There's a more brief transition to these more positive neodymium and lower strontium values. So that suggests either more trans-Himalaya erosion, so from those higher orographic areas or elevation areas, or more influence from the Deccan traps. Because those two sources have very similar isotopic compositions, we kind of need more information to distinguish between those two sources. Because if we were to interpret that because these two units are in very different areas, the interpretation of what that would mean with regard to the monsoon would be very different. But I can kind of, based on other records from this area, I can make a hypothesis on what it would mean. And I suggest that it's more erosion from the Deccan traps. So this can be caused by a shift of the intertropical convergence zone. So if this ITCZ were to shift southward, this would cause more precipitation over peninsular India. So we would get more erosion from the Deccan traps to these two sites. And these types of shifts are seen during glacial periods, so when the monsoon weakens. So that's consistent with other records that show more aridity during this time period. And then from kind of 3.5 million years ago to present, we see an increase in the overall variability of the isotopic records. So we have much larger swings between the two sources that occur much more rapidly from this time period. And I believe this reflects a link to glacial interglacial cycles. The resolution of this record can't resolve these GI cycles, but there is some evidence from these same cores that look at these changes in higher resolution. The variability of previous records are shown in green. These are kind of the higher resolution sediment records that are able to resolve those glacial interglacial cycles. So these records show that there is a link between the provenance and the glacial interglacial cycles. So I think that's just what this is reflecting. I'm just not able to resolve that because of the resolution. So just in conclusion, the sediment transport processes that tend to affect the bulk sediment records seems to be mitigated if you use this clay fraction. And these clay isotopic records are dominated by processes that are linked to provenance. And then 9 to 5 million years ago, we have an overall decrease in monsoon strength, causing more erosion from those granitic sources in the lower elevation Himalayas. And then 3.5 million years ago to present, we see this overall increase in the variability of strontium and neodymium, suggesting a link between the monsoon strength and glacial interglacial cycles. Kind of in the future, I'd hope lithium isotopes would kind of help clarify this link to chemical weathering intensity and monsoon strength. So that could be done on the clay fraction, as well as kind of additional provenance work to distinguish between the Deccan traps and the Trans-Himalaya. Lastly, I'd just like to thank the Monsoon Seminar Series Organizing Committee for having this space to kind of focus in on the monsoon and for inviting me to speak. I really appreciate it. As well as my collaborators and various funding agencies for helping out with this data. And with that, I'll take any questions.
Thank you very much, Sam. Very interesting presentation. Now we open the floor for questions. Cecile?
Yes, hello everyone. Thank you, Sam, for this very nice, very interesting talk. I have actually a couple of questions, but perhaps I start with the first one. So you showed the relationship of the delta strontium, so the strontium difference between the clay and the silt fraction or the bulk fraction. And I remember reading recently an article from Germain Bayon where he uses that to trace chemical weathering. And I was actually wondering if there's any kind of such relation, so such control in your record.
So you're saying the difference, like this value, the difference between the clay and the bulk is correlated to
yes,
chemical weathering?
That's a very recent article from Germain Bayon in, I think, chemical geology or something like that.
Yeah, that's interesting. I haven't got caught up with that paper, so that would be interesting to read and look into. Just kind of looking at potassium aluminum, which I know is affected by a lot of other things, but that isn't correlated with the difference. But I did kind of have a theory that I would have liked to look into more, that kind of the sediment transport, as these sediment transport processes affect the clay and the bulk. I did have a theory that like monsoon strength has an effect on that, because you have more erosion, and that allows the larger sediments to kind of move faster through the system because you have more water moving through, so that would decrease the difference. But I didn't have enough data to kind of look precisely into those relationships. That's interesting. Yeah.
It's actually really complicated generally, because you have this interaction between erosion and the fact that you create then some new surface for weathering to kick in.
Yeah.
So you have this kind of feedback process between these two. But you have the record, and the place is just really great to test it. So, the other question, if I may ask another quick question, is about. I was really intrigued by your the fact that you are looking at the effect of diagenesis on your record, which I found extremely interesting. Especially, it's very rare to see pore water data of strontium, and I was wondering in what way that could affect your clay strontium. Is it that you form new clays? I don't understand the process.
Yeah, so like forming authigenic clays could kind of reflect that pore water value, but we didn't see that link between the pore fluid and the clay. So I don't think it's affecting that. Rather, I think it's the opposite. I think the clays are changing, or the sediment is changing the pore fluid values, especially in this area here.
One little suggestion on that is that, there's this ongoing debate about leachates, so ferromanganese leachates or oxides formed on grains, and whether they are influenced or not by pore water. And once again, this is one of the only time that I see a record of strontium isotope in pore water, and I think there you might have really a chance to check actually.
Yeah.
If your leachates are influenced by the pore water composition.
Yeah, it's a good idea.
I don't know if you have like time around the horizons where you see the changes.
Yeah,
you could leach your sediment and see what kind of value you get. It's just that it popped into my mind. And I thought, oh, nice.
Thanks. That's a good suggestion.
Thank you very much.
Thank you.
Thank you, Cecile. I see Rasmus Tide has a question.
Yes, Samantha, thank you very much for your nice presentation. I have a question. You pointed out that and maybe I missed your arguments, that between 9 and 5 million years ago, you see that the monsoon is weakening, and that's your main reason for that you erode more of the southern front of the Himalaya. But at the same time, we know that there's a major tectonic reorganization going on in the Himalaya, and you more or less start with one of the activity of the so-called MBT, the main boundary thrust, and you uplift new totally compartments, what will affect the erosion also on the system. So how could you differentiate between the potential tectonic signal versus the monsoon signal?
So I think that would take more work. I did look at at the specific timings of these events, and I know it's hard to have specific timings, but they didn't correlate with the exact changes that I was looking at. But I would think that looking at the lithium isotopes, which have a more chemical weathering signal, would distinguish between that, but that's future work, of course. But yes, definitely need to be kept in context of the tectonic regime.
Thank you very much.
Yeah, thank you.
More questions, anybody? If not, thank you again, Sam. Next week we'll have another talk on weathering and erosion from Christian Franz Lanord. We'll be back on Schedule B. So see you next week. Thank you, Sam.
Thank you.